Pleased to introduce Vartika Singh from Cloudera. Vartika has over 15 years of experience in applying machine learning techniques to areas such as image processing, ad bidding optimization, and biometrics. Her current work is to create efficient pathways for data at large scale to easily apply machine learning techniques. She will be presenting a talk titled Deep Learning Frameworks Using Spark on Yarn. Please join me in welcoming Vartika.
Hi guys, I'm Vartika Singh from Cloudera. As you can see, I'm a field data science and architect. So, Eyal did a good job of introducing me, thank you. So I have been working in applied data science, applied machine learning before it was called data science, and my past is mostly like generating in-house, constructing in-house distributed frameworks to do image processing, do some kind of analytics based on images, ad optimization, increasing the targeting funnel size for retargeting, so on and so forth. And recently, actually 3 years ago, I graduated to Cloudera, and I say graduated because it is really big data in real sense, and I work in field. That means I work with other customers. Some of you might be our customers, and the most recent thing that we're seeing is migrating the machine learning workloads to cloud and on-premise hardware. That essentially means like coming out of R, Python, your laptops, and going into like really large-scale computing machines. And the focus of the talk here is deep learning frameworks using Spark on Yarn. And one of the reasons, obviously, is because we are a Hadoop vendor. So I have to do things which are relevant to what we do in terms of Cloudera, Hadoop, and the related ecosystem. But things that I have to do compared to like what is needed out there in the field in terms of computational complexity, amount of resources, and the amount of cost which is invested in things like deep learning. And those are the areas of things that we're kind of researching in-house and trying to deploy on scale at sites, because this is kind of evolving. So feel free to interrupt me in between, ask questions. It's kind of free format, and I will be discussing things that we are doing on site. And this is a combination of research and practice, so nothing is hard-coded, but this is something that we do out there and like excited to share with you. So this is my favorite picture kind of thing. I put it in almost all the talks that I do related to machine learning, and it's like this is Alice and Cheshire Cat. It's kind of basically like there's so many algorithms out there, and people ask like, what do we do? Where do we start? And the idea is to just get started. A typical machine learning pipeline. And when I say machine learning, deep learning is a subset of it. So as we all know, like maybe a little over a decade ago, deep learning was just known as neural networks, or MLP, multi-layer perceptrons, and there was this problem of vanishing gradient, where the error would not propagate further in order to have a meaningful learning possible. And due to certain breakthroughs, Geoffrey Hinton and all those famous people who did a lot of hard work and persisted, now it's possible to have like thousands and thousands of layers and millions of parameters in one neural net to have some kind of significant kind of some meaningful output. So this is, when I talk about Yarn and Spark, I'm actually talking about the whole ecosystem. I'm actually talking about the whole pathway, because we are not just talking about, a small set of system, a small set of data, and be able to do deep learning. There are so many frameworks available nowadays which have kind of reduced the distance between a practitioner and a neural network framework. So you have TensorFlow, you have Theano, you have Caffe, and everything is well documented. So somebody who is not actually a PhD or a postdoc, that whole distance between that thing has gone away. So it's easy, having said that, it's easy to like implement something. So this is a big data framework. This is a big data science I'm talking about. Big data has been around for a long time. So there's the raw data. So I will take an example of cybersecurity. So your raw data could be collecting data from all over the world. Your raw data could be your viruses, your exe files, your certificates, DNS, NetFlow, multiple versions of NetFlow like V8, V9, evolving all the time. Having to collect all that data, that can be like terabytes of data in a day. Be able to clean it, merge it, extract, make some sense out of it, and then do some data science, which can involve many things. Create the validated ML models, and then you're talking about a batch architecture or a streaming architecture. And once you create the models, Then you have to do ongoing data ingestion, which is kind of scoring based on the models that we have created. And Spark World nowadays, Databricks came out with the concept of transfer learning or Spark deep learning, if you people have tried it. It's like, there's like you download pre-trained models, use Spark's pipeline of deep learning to read those models, which basically peels away the last layer, and it's using the features from those last layers to, like, I have trained on this model on different kind of animals, now let's be specific to dogs, and say whether the picture contains a dog or not. So there are quite a lot of options available, and we'll be going through that. But a couple of things that I will highlight is like what are the basic problems which you face in terms of computational complexity, what you should consider when you try to use different frameworks. In the end, I will spend about 5 minutes talking about what frameworks we tried, not giving preference to any framework, but there are different components in terms of optimization. So as we all know, machine learning as a whole, including deep learning, is all about your data, your optimization function, and your cost model that you're actually optimizing on. And since when we talk about optimization, we are talking about taking the parameters, sending it across nodes. There's a lot of network activity, lots of shuffle happening, lots of I/O happening, how to minimize and optimize that. And these deep learning, there have been a recent spate of articles that Hadoop has kind of failed deep learning because it's not really built for those kind of deep learning metrics-based optimization, inversion problems. So yeah, let's get into that. So if you guys have read, this book was online for a long time, and it was awesome that they made it free. It's by Ian Goodfellow. It's called Deep Learning. I think it's called Deep Learning. This is one of the pictures in the 5th chapter, 4th chapter. I love this one. The idea is like kind of gives you a very clear idea of, and it kind of lays the basis of training on a large cluster basis. And everything I'm talking about is in like a production level job. So these are your traditional machine learning that we have been doing, like logistic regression, SVMs, or any linear regression algorithm. And you design the features. The most popular one is like NLP based, where you have these documents, you have bag of models, you extract the features. It's all hand design. And this is representational learning, and that's what all deep learning is about. Deep learning is able to extract the features, so you throw in all the images, and the first layer would do something. It's a very simplistic description. First layer would do something like identify the pixels, second layer would identify the edges, third layer would identify the shapes, and then it would be objects, and then here, voila, this is your image. So something as simple as that. So going forward, kind of makes sense when we're talking about resource management. We are talking about in a typical Hadoop ecosystem, people have things like Impala, Hive, Spark, Scoop, Flume, Kafka. Security, this can be HDFS, this can be S3, this can be Kudu, anything. It kind of makes sense to not have to move data and everything around, do your feature engineering, do your data analysis, and just feed it to deep learning networks. And so I'm putting in Cloudera Manager because I work for Cloudera, so that's like basically one essential kind of ring to rule them all, managing all the nodes that are running around. And for a typical client or typical customer, this is the kind of framework that we end up evolving. So if you can see that, the first diagram that I showed, it was kind of, you have data engineering. We started 5:10, right? Not 5? Yes. So we have data engineering, which is all about metadata, feature extraction, filter. We talk about a common strata of hard disk layer, where the data is something we just flows back and forth. And there is a data science exploration component, and that's one of our in-house version of data science workbench. So a lot of people like to use Zeppelin and Jupyter, and that's all version of like being able to interact with the cluster using a notebook-like environment, be able to write your code in any version of R, any version of Python. You can do your custom kernels using Dockers and all orchestrated using Kubernetes. And then just use the live data ingest scoring method and do the scoring of the data. Any questions so far? All right. So now, like meat of the topic, deep learning at scale. So since there was this breakthrough where it's possible to have like thousands of layers and millions of parameters, and the first network came out from Google called Disbelief, which had about 16,000 CPUs in 1,000 computers. It's quite expensive. And there is still a lot of question about like how do you scale it, like keep scaling it. Like right now it seems like it's huge, but maybe 5 years from now, maybe even a year from now, it seems like it's a pretty small ability to be able to do that. Maybe you want to scale up. And for a typical shop, like right now it's Google's and Facebook's and everybody in the world, but the people I deal with, they have like resource for say 10 nodes, 100 nodes, and how do you do learning in that kind of situation? And leverage you already have Hadoop clusters. There was one question from a genomic shop that I already have 500 nodes. Why do I need to buy more GPUs in order to do something like deep learning? Or do any kind of training? Why can't I leverage those resources? So the more there is breakthrough, basically it means you can add more million number of parameters, or more number of layers, and the problems like visual recognition tasks, the problems like speech recognition, they have been pretty much well done and well scaled at, like your self-driving cars, your Facebook images, and so on and so forth. But your daily, everyday problems like indexing, tagging, parsing, those problems are still out there. Cybersecurity, those problems are still being solved on basic commodity hardware. So this is basically a readout of what I just said. Like you can, because of all the unsupervised data and the concept of representational learning, there's a lot of problems that can be solved now. And that problem of like 1,000 machines and 16,000 CPU cores. Yeah, I said 1,600, right? Sorry, 16,000 CPU cores. Recently, there has been a paper by same group of people or overlap of a group of people who did the same kind of work in about 16 machines running with only GPUs. So this is the biggest debate we have out there. Like, what is the comparison between CPUs and GPUs, and how do you scale it out of based on that? Bless you. So distributed learning, when to do. So another use case that I see out there is like someone would say that these frameworks are there. TensorFlow, when they first released their open source library, it was not distributed. That was a version that was printed out, sent out. Then TensorFlow came out with a distributed version. Then TensorFlow came out with the support for HDFS. That means you can read and write from HDFS. But even with those, like a lot of shops that we see out there, like you said, shops, like a lot of people who are like, they have these endeavors that I want to do deep learning. And they have this cybersecurity data, healthcare data, text data. How do I do the analysis? And the best possible way for them is buy a high-performance computing machine, stay within one machine, forget about the networking infrastructure, use a high-speed bus, and use the GPUs and do the training. They are not leveraging their existing cluster, existing resources, or the ability to buy 4 more nodes with GPUs and do the training at much larger scale. So let the training run for 21 days because it's training, it's offline, and then after 21 days I will do the scoring and see how well my learning did. And then go back and do for 21 days again. Come back and go back and do for 21 days again. And instead of that, if you're able to do the processing on 4 nodes, you're able to speed up your training process. And it's like more iterative, faster iterations and explorations and inference. So the last phrase, that's what happens quite commonly. Continue to train your networks on a single machine. And I mean, it's kind of a non-scientific thing to say, more like human aspect of it, but more often than not, when there are data scientists in a company and they want to explore something deep learning related, usually they need to prove that why do they need these resources. And when there is a certain person who's responsible for buying the nodes, like why do you need deep learning? Deep learning is supposed to be for like the Facebooks of the world. And so how do you prove those things? And this is how you prove, but not everybody has high performance computing machines. Spark and Hadoop systems come to the rescue there. But training speed is still a problem, and how do you scale it out? So there are 2 concepts, like there are 2 ways. First obviously is like people have this concept of getting some kind of algorithmic advantage by using more locally connected networks. So instead of having too many connections between 2 layers, just use pure connections so that you can train faster. And you have the smaller the number of parameters, smaller the number of layers, the size of the model is smaller. So you can fit it within a That's one option. The other focus of research is scaling out and scaling up. The scaling out is like one axis where you are using multiple machines in a large cluster to increase the computing power. The second option is leveraging general purpose graphics units, and that's very common. The problem with general purpose graphics processing units is that it works very well. So GPUs are designed for high memory bandwidth, but they are not very well they don't work very well for high memory access points. So that means when the data is being transferred between CPUs and GPUs or between one node to another node, when that need occurs, that means your processing slows down quite a lot. So ideally, GPUs, that's when I say that people focus on high performance computing machines when using high speed bus to leverage on the cores and to transfer the data between different cores within the system. But the whole infrastructure or the whole framework should be able to take care of these two options, whichever you want to choose. And we'll go over those. Questions so far? All right. So with respect to the large number of training examples, large number of layers, a lot of focus has been done on optimizing on GPUs. So as I said, like GPU approach works pretty well when your whole model fits within the GPU. So that there's no need to pull the data out and put the data back in. As in any Spark level processing where you have to avoid the spread to disk or shuffling between the data sets. So the idea is to use the GPU effectively. People focus on reducing the size of the data or the parameters so that the transfer between CPUs to GPUs and between the nodes is not a significant bottleneck. So as far as small problems are concerned, like acoustic modeling or speech recognition, they can be fixed pretty fast. But like high parameter problems like image recognition, that creates a problem.
So can you give me a couple of examples on when this technology means what kind of use cases where you will go beyond?
Yeah. So the question is, what kind of use cases where you would like kind of start crossing that kind of boundary? So one is obviously you have to benchmark, but there are two different kind of parallelisms that people try to, or researchers try to obtain, or the frameworks who are implementing this, like TensorFlow or Caffe or Piano. They implement different ways of parallelizing the problems. So if you understand what your data set is like, what your problem is like, and what kind of method you're using to parallelize it, you would kind of an idea that this works better or this works not that great for me. So, and I will go over those in a bit. You have a question? So this comes down to what you were asking. So there are two primary ways to where people try to attain the parallelism. And parallelism is something like how to execute multiple threads of the execution together in a certain way. And it's kind of a conflicting. So usually in the Spark world, what it means is that you're giving 4 cores to one executor, and you have 5 executors overall. And if you're able to distribute the data in such a way that overall you have more than 300 partitions, your data is going together 5 into 4, 20 times. So 520 times subsets of data are getting processed together. On the other hand, if you have 5 executors and you have 2 cores each, the parallelism goes down by a factor of 2. That means the subset of data which is getting processed together has gone down quite a lot. So the queue of the data which is waiting to get processed is higher. And if you increase the number of cores by a factor of 3, the queue kind of significantly reduces. But using the same amount of resources and same amount of memory, if available, to speed up your execution. So there are, based on that concept, there are two parallelisms available. One is within machines, that is multi-threading, and that's where we come into the realm of GPUs. And then there is across machines, that's where we come to the framework of, say, NPI or AERON, AERON. They are frameworks for like being able to pass messages in a larger chunk and more effectively and faster. And how do you kind of compromise between these two? So for example, convolutional neural networks. They have the concepts of large number of layers and large number of nodes. And there are 2 dimensions that the parallelism can be obtained. One is pivot on the model, and that's called model parallelism, where you split up the models in many chunks, and different nodes are processing different layers of the model. So if you have 10 layers, 2 of the layers are being computed by one node, 2 of the layers are being computed by one node, so on and so forth. So the work has been kind of distributed across nodes. But when you talk about data parallelism, you're pivoting on data. and that's what usually Spark does. And the idea is that if you have one RDD, that's the basic idea of Spark, or one data frame or data set. The idea is that the one basic partition of RDD should fit within your task. And task is defined by the code. So if one executor is launched with 4 gig of memory and 4 cores, you have a parallelism of roughly 4. But the amount of memory available to each task goes down quite a lot. That means the amount of data which should fit within the task should exactly fit within the particular task. So if you're divvying up 4 gig of memory with 4 cores, approximately 300 MB is available to each task. That means each partition of the RDD should be able to fit within that task. So when that happens, that particular mode of operation is called data parallel. Now, data parallel. Excuse my pronunciation. So, model parallelism and data parallelism. Yeah, I have I pronounce it differently. Okay, so first is model parallelism. So, different machines in the distributed system are responsible for the computations in different parts of a single network. So, for example, each layer, which is a neural activity in the neural network, may be assigned to a different machine. But in this case, this also works well as long as your whole model fits within your GPU memory perfectly. But the idea is the output of one layer, so you're talking about forward propagation and backward propagation. So the output of one layer is going to interact with the input of the next layer, and vice versa. That means there has to be some exchange of parameters. The exchange of parameters in this case are kind of less. As compared to the amount of exchange of parameters which happens in data parallel mode, which we will discuss in later. But so the bottleneck here is communication networks. Like how are you communicating in between? So for example, if I split up I have 1 gigabyte worth of parameters on which I want to do my computation. My GPU based model will take approximately, I'm just putting out a number there, say 8 milliseconds. It's that fast. But now I want to exchange that information with my brother or sister node. That would take 8 seconds. And that's my bottleneck. And the second case is data parallelism. In this case, there has to be some kind of synchronization between model parameters. And most of the frameworks out there, like model parallelism in theory and logically, actually it works better. It's supposed to be more performance. It's supposed to be more performant as long as the size of the network is huge. So if you're training images, you're training lots of cybersecurity data, something which is like huge in number and involves a lot of parameters and a lot of layers, model parallelism works far better because the amount of data you're exchanging is quite less and GPUs really shine in that case. But if the amount of data is pretty less and you're doing like POCs and those kind of operations, data parallelism kind of works better. It's easier to implement. So almost all the frameworks you will see out there, they have some version of data parallelism implemented. Also, and they are fault tolerant to a certain nature. So if you think about it, your data has been distributed into many parts. And if this operation on this particular subset of data fails, that operation can be re-executed without loss of information across different nodes and different operations. It's like functional paradigm model, like when you do map reduce or spine jobs. So for a common person like me to be able to use that particular model and to be able to use that particular implementation in a framework like Yarn or Mesos or just Spark is far easier than thinking about model parallelism, where I don't have GPUs available usually. And yeah, basically that. And most of the frameworks don't have that implemented, and we will go through which have them and which they don't have. Questions? So usually the Spark-based systems, they work on the concept, since most of the work and most of the research due to the availability of resources and more easy productionizing, more convenient productionizing has gone into the effort of data parallelism. The research has been done in this area quite a lot. So, well, end of the day, what happens is the copy of the model is in each node. So if you have 10 nodes, each of them have the whole complete copy of the model. That's the basic idea. Then a subset of data is given, a different subset of data is given to each node. Each of them performs a local computation on that data. And then end of the day, each of them's responsibility is to synchronize amongst each other. So different versions of data parallelism differ in the method of synchronizing those parameters amongst each other. Those parameters can be huge in number again, and that again becomes your communication bottleneck. But there are many ways to do it. There are many workarounds to speed it faster. So one of the workarounds is parameter averaging, a concept of a parameter server. That's like a concept of either centralized or uncentralized. But the idea is that you initialize the weights across all the nodes, do the local computation, and then do the synchronization on a common parameter server, or just do some kind of averaging, or do some kind of gradient-based update method. And in the end, the other two options are synchronous or asynchronous. In case of synchronous, if you have multiple Spark executors or if you have multiple jobs running, the lowest one becomes your bottleneck. So if anybody has run a Spark job here and you have fired off like 10 executors, you might have noticed that case where all 9 of them are complete and it's waiting on just one task forever. And those are the optimizations that you end up doing here. And usually what we recommend, even in case of like all the experiments that we did in case of Spark and Yarn, we did it in cloud and we did it in on-premise. On-premise was kind of harder because for computational costs we just get access to AWS or GPC. Regardless of what's available, like leveraging these libraries. So if you're using a GPU-based machine, your processing time goes say 10 times faster. We are going to release the numbers. But right now, like just on average, say it goes 10 times faster. Then we use these GPU accelerated libraries, your computation goes even 10 times faster. So what these GPU-based libraries do are they take, so NVIDIA knows their architecture better. If I'm using something like Nirvana from Intel, they know the architecture better. So if I leverage their optimization libraries, which write matrix-based operations, tuned and optimized to the architecture of the parallel hardware they have, there are multiple benefits that I obtain. One is there's a specialization, so that they are focusing across the evolution of parallel architectures, across different versions, and the framework developers, like people who are writing Caffe or TensorFlow or Piano, their job is kind of separated. There's a clear separation of concerns. All they have to do is invoke that API, write their programs, and these developers are behind the scenes leveraging the architecture to write things like convolutions or pooling or hyperbolic functions to make things faster. The second is, we already talked about CPUs, GPUs. I'm not going to put too much amount of time here. But again, at the end of the day, the bottleneck is I/O and network. And there has to be a balance between CPUs and GPUs. So when you're deciding like, okay, I have this data set and I want to do GPUs, you can't go all out with GPUs because you still need some processing time for processing bandwidth for serialized operations, which actually CPUs are supposed to be good for. Since we talked about communication costs, and I'm just using AWS, not saying that we have a preference or demonstrated preference for AWS, just an example because we experimented a lot on them. So what you use in cloud in terms of your EBS optimized instances. So nowadays we're talking about virtualized environment. In virtualized environment, you don't know what piece of hardware you're getting from out there in the wide world. So the EBS optimized instances kind of give you this guarantee. I should go to the next slide. They kind of give you a guarantee in terms of IOPS, and if you don't pay for that IOPS upfront, then there is no guarantee, and as you scale the amount of money, you get more IOPS. Along with EBS, these are elastic black block storages, if people are familiar with it. So when I spawn off an EC2 instance, those are the instances that are attached to my network system, and they give you network guarantee depending on what you configured for it, and they give you IO guarantee. On top of that, the EC2s are elastic compute nodes from AWS, and something like that is available from Google Compute as well as Azure. So again, no comparison there. But the idea is that there is a geographical location for all these instances. So in case of AWS, these nodes are launched in a certain availability zones. So if your node is within, say, Western Virginia, you probably want rest of your nodes within Western Virginia as well, because that gives you kind of network guarantee. Kind of. Then there's maximum transmission units. So there's a concept of virtual private cloud. As long as you're launching your instances within the virtual private cloud, you get a guarantee of 9,001 transmission units within one frame. But if the frame is going outside of a VPC in order to save money, you say launch network or instance somewhere else, that means those packets will be broken. And that's the extra cost to incur. Along with that, there's a node size. The larger the node size, the better the network guarantee, and so on and so forth. I'm speeding forward. The most important part of the talk. So these are the frameworks that we tried on Spark and Yarn. So Caffe 2 was recently released. I talk about Caffe 2 because it was recently released by Facebook. And they implement data parallel mode in synchronous stochastic gradient descent. And that essentially means that it will run for something like your speech monitoring or speech classification or image classification rather slowly. If you want to run something like heavy in terms of image synchronization, you probably want to go back to old school Caffe, which is actually made for model parallel implementation, but old school TensorFlow, it implements almost all synchronous, asynchronous entities in data parallel mode, as well as a combination of data parallel, model parallel computations in CNN-based implementations. Caffe on Spark and TensorFlow on Spark have been released by this group from Yahoo, which kind of do an interfacing with Spark on these libraries using JNI, and they use MPI-based communication. Both of them work pretty well, but both of them offer only synchronous and asynchronous versions of stochastic gradient descent in data parallel mode. SkyMind has DL4J, which is completely tested out for Spark. It works pretty well, but they are also working on asynchronous gradient descent and moving away from Spark, using Aeron for message processing and computation. And this, I guess, I already talked about. I will end up here. Any questions? There's a lot to cover, I'm sorry. Like end of time. So if you have any questions, feel free to send me an email or, yeah, I'm at Cloudera.